now that we know how to draw Lewis structures and determine the three-dimensional shape of a molecule using VSEPR theory, it turns out we can also determine whether or not a molecule is polar based on both the three-dimensional geometry and, of course, differences in electronegativity. Remember that a bond, we figured out a bond is polar or not if the difference in electronegativity produced a dipole moment causing a partial negative charge, an excess of electrons, high electron density around a more electronegative atom, and an absence of electrons, which causes less shielding of the nuclear charge and a partial positive charge associated with the less electronegative atom. Okay, and HCl would be an example of a polar bond. And because that's the only bond that exists in the molecule, we can also say that HCl is a polar molecule. Now, determining whether a molecule with more than two atoms is a polar molecule not only depends on differences in electronegativity and the culmination that would culminate in a polar bond, but also whether or not the geometry is in a configuration that is conducive to a polar molecule. And here's what we mean. Okay, if we take a look at carbon dioxide, we can see that it is a linear geometry. It has two electron groups. They happen to be double bonds, but nonetheless linear geometry. So we know that this bond angle is 180 degrees. Okay, we also know that oxygen is more electronegative than carbon, so there's a dipole moment set up attracting electrons towards the oxygen atom. But as you can see here, there's an equal attraction towards the other oxygen atom. So what happens is, you can think of this as a tug-of-war for the electrons. Each oxygen is pulling in equal and opposite directions because we know it's 180 degrees apart. So if you look at the electron density plot of a carbon dioxide molecule, there's no distinguishable end of these of this molecule. There's no partial positive charges, there's no partial negative charges. So even though there are polar bonds, this is not a polar molecule because the molecular shape causes the dipole moments to cancel out. Conversely, if we look at a water molecule, we know that water molecule is bent, not linear. So the dipole moments between the oxygen and hydrogen have a net dipole moment towards the oxygen atom. They do not cancel out. So this has a polar bond, and it is a polar molecule. In the lab, we can go in and we'd actually observe a partial negative charge, a partial positive charge on the hydrogens. There's a net dipole moment because there are polar bonds, and the geometry doesn't cause them to cancel out. There's a net dipole moment. The same thing is true for ammonia. Because it is trigonal pyramidal and not trigonal planar, it causes it to be a polar molecule overall and not nonpolar if it was perhaps trigonal planar. So let's take a look at a few more examples and think about whether or not they would be a polar molecule or not. Okay, what about methane? Okay, we know methane is CH4, and we could draw a Lewis structure like so. We could try to draw a three-dimensional structure, CH, these three atoms in the same plane. We've got one hydrogen coming out at you, one hydrogen coming away from you. And it turns out we actually didn't even need to do that. If you do look at the delta En for the carbon-hydrogen bond, it was 0.4. That is a non-polar bond. And so, since there's no polar bond in this molecule, this automatically eliminates this from being a polar molecule. It is a non-polar molecule. Okay. What about a similar molecule, CCl4, carbon tetrachloride? Okay, CCl4 would look like, just like methane in that instead of hydrogens, it has chlorine atoms, but it takes on a tetrahedral geometry because it has 4 electron groups. Now, if you look at the difference in electronegativity, it turns out that carbon and chlorine does produce a dipole moment, or polar bond. There's a polar bond between all of the carbon and chlorine molecules. But it turns out that carbon tetrachloride is a non-polar molecule. So why is that? Just like carbon dioxide, the geometry of this molecule causes all of the dipole moments to cancel each other out. Instead of just playing tug-of-war with electrons in a straight line, we're all pulling at 109.5 degrees, all in opposite directions, all at the same strength, so the dipole moments cancel out and produce a non-polar molecule. Okay, what about another atom with a 3? So we already saw that NH3 was a polar molecule. Okay, what about BF3? Okay, boron trifluoride. Okay, boron has 3 valence electrons, and if you remember, it is one of the examples of an incomplete octet. It can form a molecule with 6 valence electrons. So BF3 looks like that. How many electron groups does this have? It actually only has 3 electron groups, and so it has a trigonal planar geometry with a 120 degree bond angle. Okay, the fluorine, being the most electronegative atom on the periodic table, definitely is going to set up a dipole moment here. Okay, it is very electronegative and attracts those electrons. But because of the fact that this is a planar molecule and all of those dipole moments are equally spaced 120 degrees apart, it turns out that BF3 is a non-polar molecule. All of the dipole moments cancel each other out, yielding no net dipole moment and hence a nonpolar molecule. So again, you have to consider whether or not the molecule has polar bonds. If it doesn't, automatically a nonpolar molecule. If it does have a polar bond, you have to ensure that the geometry does not cause those polar bonds, those dipole moments, to cancel out, yielding a nonpolar molecule. If they don't, it is a polar molecule. And so here's a table from your textbook that illustrates all of the various geometries that exist depending on the number of electron groups and, of course, the number of bonding groups versus lone pairs. In each of these, you can figure that out in the geometry based on VSEPR theory, and again, utilizing the idea of polar bonds, dipole moments, and whether or not they cancel out, you can determine any of these molecules are polar or not.